I think it should work. Okay, so let me start by what I think is really the big question. And again, it has to do with the fact that in machine learning, you try to learn tasks with high-dimensional data. And in this talk, for concreteness, I will mostly be thinking about, say, binary classification. Okay, so our usual example of cats and dogs. And so you're given many pictures, maybe 1 million cats, 1 million dogs, and you're allowed to learn from them. And then you try to guess what is on a new picture. And the big problem is that if you think of it, a picture is a very highly dimensional object, right? Maybe if it has 100 by 100, maybe 10,000 pixels. Even if you're black and white, so it's an object which is in dimension 10,000, right? And in large dimension, you have a geometrical problem, which is the following. So in this talk, P would be the size of the training set. So if you give me P data, P pictures in that case, if you're in large dimension, actually you can't sample space. So the distance between neighbors essentially is constant. It grows like the number of data to the power -1/d, where d is a dimension. So if you think about d being even in the hundreds, and it can be much larger, I mean, this is essentially not going to change. So you're not sampling space. And because of that, you can show that if you make just mild assumption on the task you're trying to learn, for regression, that it's just a Lipschitz function or something like this, well, then you can prove that in general you won't do better. I mean, you won't learn it. So the tester will vanish with the power law of the size of the training set. But again, the exponent would go like 1/d. This is d. So again, in large dimension, essentially you're not learning. Okay? So this is the dimension. So that's the key question. So if you can learn data, and we know that those kind of data are learnable, they must be highly structured. And there is still no agreement on what is this structure exactly. That's true for any machine learning scheme. If you think about deep learning, there is this intuition that this method is very powerful because it builds an interesting representation of the data. So I'm sure you've seen those pictures. So after training, in the first layer, maybe you're going to create neurons that detect low features like edges, but if you go deeper, then you have neurons that respond to more abstract features, maybe the face of a man or something like this. It's beautiful. It's similar to what our brain is doing, but there are many questions associated to it. And one that was discussed, I think, by Nati and others in the first lectures is it always the case that you actually learn features, learn interesting representation? And I think you already know that there are different training regimes for those algorithms where in some regimes they don't, in others they do. And so you can ask the question of, is it always beneficial or not to learn those features? One idea, and for modern architecture, I think we believe that it's actually very useful. One intuition as to why it may be useful is that you may be able to build a representation of the data which is much lower dimension, therefore maybe dealing with the curse of dimensionality. And empirically, there is evidence of that. So you can try to measure the dimension of the manifold on which data lie. It's called the intrinsic dimension. I'm not going to enter into any details, but if you use those kind of techniques, actually people do observe that after training, the dimension of the representation of the data is actually lowered a lot. And in this talk, I will take a slightly different perspective. So that suggests that actually what those nets are doing is really getting rid of some information on the data. But what is this information exactly? So I will take a physics viewpoint of perturbing a bit the input and see what's not being transmitted. Okay, this is essentially just to introduce my notations. So for me, P again is the size of the training set. Okay, X are the pictures. If you want Y a label, for binary classification, it's plus or minus. N will be the number of parameters. The width of my network is H. And in this talk, when I think about over-parameterization, increasing a lot the number of parameters, I'm thinking about fixing depth which I call L, but really increasing the width of the network, right? So N actually, in this case, is quadratic in the width. And okay, I have some empirical data to show you, and I think most of them are for neurons that are actually ReLU neurons. Okay, so you heard a lot about how we train, we build an empirical loss. It's a sum on all the data of some function. For binary classification, it's just a function of the label yi times the f of xi. You would like this quantity to be positive, and so you build a function, you choose a function L that's decreasing. And you can look at a softmax, something that's exponentially decreasing, and we also do, but often we like to take another popular loss, which is a hinge loss. So essentially you have a margin. If this product f times y is larger than 1, this is 0. This quantity really goes to 0. If it's not 1, then it can grow quadratically or linearly. Okay. So there are, if you look at state-of-the-art networks and you choose one loss or the other, we find very similar performance. But why we like this are two reasons. One is most of what I'm going to tell you will hold for the two losses, but there are two reasons. One is conceptual, just for the first 10 minutes of the talk, is that if you do that, when you take the loss being equal to 0, it means that all of those terms are exactly 0, and it means that you're satisfying some constraints. The product f times yi has to be larger than y for all data. And this becomes sort of problem of satisfiability of constraint. And in physics, we like to study those problems too, so we can think about making analogies. There is a more mundane, simple reason why we like such losses is that empirically, at some point, the loss can reach 0, and then you just stop training. Otherwise, you have to decide on an additional parameter that tells you how long you're going to train. All right, so then what you do is that we think about gradient descent. In fact, many of the data I show are approximation of gradient flow, where we adapt time step to be close to gradient flow. So what you do is then you choose randomly your initial weights, and then you do sort of descent in this landscape. And now there is a question of what is this landscape, and I will be brief because I think you had an entire lecture on that. And the point is that you're in large dimension, and this function has no reason to be convex. So in general, you could worry that when you go down in this loss, you will get stuck in a local minimum. So are you stuck or not? So this is immediately raising the question of the geometry of the landscape. And so what is observed is that if you don't have many parameters, the dynamics looks very glassy, and it seems that you can get stuck. If you have many parameters, then both empirically, but also mathematically, you have theorems that actually use a huge number of parameters that tell you that now then the landscape becomes very flat and you can reach a global minimum. And so one question we have been interested in is what is actually the transition between those two kind of landscape. Okay, so here I'm going to show this data, a phase diagram. That's for MNIST. It's coming from this paper that reviews what we had done for 2 or 3 years before. And in this paper, we will show CNN on CIFAR 10 and so on, and you get very qualitative data, qualitatively similar data. Here, it's just gradient descent fully connected to 2 hidden layers on MNIST. So to think about this question empirically, we think about 2 parameters as being important, and I think they were discussed quite a bit also at least by Nati and maybe Andrea as well. One is the number of parameters, useful to think about over-parameterization, but the other one is the scale of initialization, which I call alpha tilde here. And the predictor that we look at is my network. I remove the network at initialization, and I multiply it by this constant. Just to remind you probably of the previous 2 weeks, that's interesting because if you take this coefficient to be very large, then your predictor, even with mild, very small change of the weight, can vary a lot and fit the data. And because those changes of weights are small, you can linearize this term. And so your predictor becomes linear in the parameters, and so you just have a kernel method, which you discussed, I believe. Okay? So this is very large alpha. So here it's going to be more like kernel methods, and here it's the opposite, it's very small alpha. So when you're very small, when this coefficient is very small, then those functions have to grow a lot, the weights have to change a lot, and then you really probe the nonlinearity of the networks. Okay, so this is alpha, this is the number of parameters. I'm going to tell you what you see on the phase diagram like that. So this is a single slide that I do on the landscape property. And what you see in black here, so I'm happy to discuss it this week. I'm around this week. It's going to be a bit fast. But so what you see here is actually the region which we will call underparameterized, where if you do a gradient descent, you don't hit bottom. The loss does not go to zero. The white region is the happy region where you actually reach the ground state. The loss goes to zero. And so in this regime, actually, you find that the landscape is glassy, and in this regime, it's flat with many directions. What we studied is actually the transition between those two. And for a physicist, this is actually, in a diagram like that, a line of critical points. So actually, there is a sharp phase transition that separates the gray from the white region. And it's called, in physics, a jamming transition. And that's the kind of transition that we have in other satisfiability problems. And so the classical one comes from studying granular materials. Think about elastic particles that hate to touch each other. They want to separate. So you also have a constraint for each pair of particles. Just like in machine learning, you have a constraint for each data that needs to be fitted by a margin. And so in this problem, you also do a gradient descent. You put randomly spheres into a box, and then you lower the energy. And if the density is low, then you obtain a solid, and it's a glassy problem. The landscape is glassy and well studied. And if it's dilute, then you can solve all your constraints, and then you have many flat directions in your landscape. Yes?
I'm a bit confused. I'm trying to understand. In the top of that, so if you go up or back, or I don't know what you call it, is it lazy? So is the top gray part, is that glassy, or is that just that is it the gradient descent gets stuck in a local minima, or is it that the local minima is global, but it just doesn't have zero error?
Okay.
Because I don't understand why you would ever be glassy when you're in the... I understand you can be glassy at the bottom, but I don't see why you would be glassy at the top.
So you don't see why you would be... Okay, so...
I'm seeing you're not going to get zero error, right? So you would see that...
So the thing is that
glassy, right?
as you approach this... Okay, I will discuss it here. When I say... actually, there is this slide. It's coming in a few slides. So that separates what's lazy and feature. I will define it. But close... And in fact, this is this dotted line here. But it has to curve up. Because close to this point, your predictor diverges. So when you approach this line, you're never lazy. You see what I mean?
Okay, so the lazy is
So
really...
so this is like that.
Okay. Okay. So you don't have glassy lazy.
Yeah, you don't have glassy lazy. Yeah. What this analogy? Okay, so this analogy tells you, it gives you. Then you have universality, and so you have some results that we knew here that can be applied there. I'm not going to enter in the details, but for example, if you look at the curvature of the landscape, the Hessian, it has interesting property in the vicinity of those critical points that you can test and actually observe in deep learning. Maybe more importantly for performance, what you have is that close to this point, the predictor diverges with some exponent, and you approach here that we think we understand. Another phenomenon that you find in critical phenomena in physics is called critical slowing down. If you're right at the transition and you try to have the energy goes to zero, it takes a huge time. And here you also find the same, that if you try to learn in the vicinity of this point, it takes much longer. And also, this is with respect to this sort of danger of being stuck in a minima, this is just telling you something not very surprising, which is if you have enough fitting parameters, if n is larger than p, then you expect you're going to fit the data. And for a problem like that, when you fit the data, well, your landscape is not glassy and you actually, hit bottom. So then there is a simple way not to get stuck in bad minima, is just to over-parameterize your network, which in retrospect may not be very surprising. But then you will think about overfitting. What of a model that has many more fitting parameters than you have data? And here what you see on those curves, so this is a double descent phenomenon that I'm sure you talked about in the first 2 weeks. This is the tester in blue for 3 values of alpha, okay? And what you find is, naively, you would expect some kind of parabola. If you have too many fitting parameters, you will overfit. And in fact, you see those curves. So they were observed actually a while back, but noticed more recently by Sachs and collaborators for regression in shallow networks, and we saw it for deeper network and classification. And there are actually 2 interesting effects. One is the fact that actually you have a cusp, so this is the worst place to be. It's close to this transition, or to have a very tiny number of parameters. And that actually has a simple explanation. It just comes from the fact that right at this point, the norm of your predictor explodes, diverge. So you have huge fluctuation, and it has a big cost. Another effect is, again, very surprising, that in this white region, where you perfectly fit the data, it's still better to increase the number of fitting parameters. Okay? You fit perfectly the data, and still it's better to increase this number. And you've seen, I think, exactly solvable models that capture that. And I will tell you just in 2 slides the simple scaling argument we came up with and tested when we found those properties. Because that's a very simple way, I think, to think about this problem. A key aspect of those curves is that they motivate one to think about what happened in the limit where the number of parameters is huge. For many data, you see that it's actually just getting better, so that seems to be the good place to be. And here, you have been told, you actually already know what's going to happen. So when alpha tilde is large, in this region, when you over-parameterize the system, as I told you, the system becomes, the function predictor becomes linear in its weight, and you have a kernel method. It's called the lazy regime, and the kernel is a neural tangent kernel that you discussed so far. So here you don't have this sort of learning of features that people believe is interesting. Still, if you have interesting architectures, CNNs and so on, those kernels that you generate by linearizing a network are actually quite good. So later in the talk, I will be discussing some aspect of what we think they do. And then you have this other regime when you initialize the weights to be very small, your function has to evolve a lot, and then the neurons are going to learn to respond to different things as you train. Okay? So you have those 2 limits, and this one is actually, the kernel limit is much better understood than the feature, it's called the feature regime, which is more nicely formulated for one hidden layer. Even there, quite many things understood, but not completely, but when you're deep, it's still a challenge to understand what this limit does in general. Okay, so let me give you the simple scaling argument. Yes?
On the previous slide, the terms of generalization error, are they comparable across these 3 initialization schemes? If so, the intermediate scaling seems to have the lowest generalization error as you keep over-parameterizing.
So maybe I should, okay, so there are many questions there. Let me see if I answer it. First of all, Maybe you've seen in class this double descent a lot in something called random feature models, which is really thinking about completely freezing. Here you see that this phenomenon is more general. It happens even in completely different regimes, very nonlinear regimes, right? And then I think you're asking a very relevant question, which is, what about the absolute value of the tester? Which regime is better? And this I will discuss. Yes. Does it answer your question?
I will wait when you discuss it.
Okay. Okay, so the point is that when the number of parameters diverges, you converge to well-defined algorithms, where even the notion of parameter, you can express what the algorithm does without referring to parameters, right? And so what happens is that when n goes to infinity, I think it's quite intuitively clear that the randomness associated with how you did initialize your weights, you know, this random initialization, is not going to matter. Okay, you have some, you take, as long as you take random numbers from the same distribution, you will get this randomness is not going to matter. But what happens is that if n is finite, then you will remember where you started from in this landscape. And that's something we worked out with Arthur Jacob and Clément Engler in the kernel case. One effect that you can isolate is the fact that your kernel will have fluctuation at initialization. And what you find is that those fluctuations, it's a sort of central limit theorem for the kernel, they go like 1 over the square root of the width, which means n being quadratic in the width, n minus 1/4. So the fluctuation of the kernel lead to fluctuation in the function after training. And when you have fluctuations that are induced by, you know, they are just random fluctuation induced by some random numbers, you pay a price for those fluctuations. And in general, this price is quadratic in the fluctuations, and so you actually get that the tester at a given n minus the asymptotic tester should, you know, vanish like 1 over square root of n. And that's actually something that, and that's a simple argument that you can test for real image data set on CNN of, you know, depth 5 or 6. That's what we did. So I'm not showing you the scaling laws for reasons of time, and also because there is a very simple measurement that can prove that this idea is essentially correct. I should also mention that in the other regime, we find the same scaling. It's quite natural, and you can prove this scaling. Eric van den Eyden and others prove this scaling in this feature regime as well. I mean, so you have both the same scaling description, both in the lazy case and in the feature learning case. A simple way to evidence that this is a key effect on real data is to eliminate it. If those are fluctuations that are induced by, you know, by the random initialization, a very simple operation you can do is, instead of looking at one network, you look at many networks and you do a democracy, right? So for example, you average the output. You take m averages and you take m just much larger than 1. Okay, so in those experiments, m is 20. So
this average is not just the initialization noise, it also averages some other forms of noise.
So what
SGD noise or some other things.
Oh yeah, so here all those data are full gradient descent, so we are not putting any SGD noise. In fact, we try to approximate gradient flow just for to make it simpler. And so in fact, there is no other source of noise that we are averaging on, right? So we're just averaging on initial configuration on the weight. Obviously, we're not averaging the weight, so we are averaging the output, which is a nonlinear function of the weight. Yes? Okay, if you do that, you can compare two curves. This is the tester of a single network that's doing this double descent. And it has a curve like that. And now this is the curve that you find for the average predictor. And what you find is that, and for image data set, we always typically, we find that. Sometimes it's not exactly flat, but essentially the curves always look like that. So you get rid of the second descent. So you can easily get rid of the second descent obtain the quality of very large n at a much smaller number of parameters just by averaging. Okay. And I mean, after that, there was an interest in having a random feature model where you can actually have mathematical proofs. And in those models, the effect is key as well. Yes?
I think I already asked you this once, but again, so if you look at these points, if I compare a model with like whatever number of parameters, and the averaging only averages 20 models. So it only has 20 times more parameters.
I remember you asked.
That does perform better than having
yeah, it does. That is, if you think about memory constraints, it's better to ensemble. Actually, that was then studied quite systematically by the Google group. And it's better because the noise decreases not like 1 over the square root of n, but like n minus 1/4. That's why it's much better to ensemble than just to take a very large system.
In terms of training time, do you have a sense? For memory, it's easier to make the statement. Training time, I don't know how you even make that statement. Do you have any sense of that?
In terms of training time, is it... so, I don't know. I didn't think about it. Well, yeah, I mean...
Yeah, but for memory, it's actually interesting.
I mean, I think they would have done it in this paper, but I should...
Okay, no.
For the feature learning regime, the ensembling error goes up a little bit. Do you have an idea?
So, okay, so here we're discussing one effect, which has to do with the kernel at initialization being random. But as you know very, very well, there is another effect, which is that the kernel, as when n is not infinite, even in this regime, the kernel will also evolve during training, right? So here we see, well, what we are saying is that this effect we think is often the dominant one when we look at data, in the sense that when you remove it, it's almost flat. But if you look at our paper, you will see for various data sets that, yes, sometimes you have a little dip here. Is it because, okay, so then you have other effects like the fact that the kernel is evolving, that's entering the picture. Is it helpful? Is it, we have little understanding of that. I mean, I do at least. Yeah. I mean, it varies on the data and the architecture, those sort of little dips that we find. Yes?
Can I ask about the initialization? Because you mentioned random initialization, but in like practical deep learning, you don't do it really just random Gaussians or something like this. So are you comparing, like, let's say, sensible practical initialization as your starting point, and maybe have you compare different initializations? Because sometimes you initialize and you cannot really convert even with this overparameterized regime. So I was wondering, maybe this is the solution to why some initialization doesn't work in practice.
Okay, so in some other talks, I show you this curve is actually the mean test error for those 20. For each of those guys, we get a test error, and then I plot the mean. And so I can show you the variance. And for those data we looked at, I mean, except if you're close to jamming, where sometimes it explodes, sometimes it doesn't, this is still a small quantity. So for most of this phase diagram, except if you go maybe, what you will find is that you get very similar results if you initialize independently of how you initialized. If you're very close to this point, sometimes you could initialize and be in the black or be in the white because of fluctuation. So when you're close to that, just like in usual phase transition, this randomness can matter. But if you're here, it doesn't.
Okay, so very quick question, sorry. So when you say it doesn't matter how you initialize, you mean you run Python?
Well, I mean, once you've chosen a distribution of the parameters.
Okay.
Once you've chosen a distribution and you sample from those distributions,
okay,
yes. But the distribution can matter, yeah. No? Okay. Okay, so now there was this other question in the audience, which is, from those two regimes, which one works best? And so you can, okay, so now in the rest of the talk, let's forget about overparameterization, okay? So you heard a lot about it in the last 2 weeks, and I think this question starts to be actually well understood. And now I want to ask a question that's much less understood, I think, which is if the number of parameters is large, okay, so maybe that's the sweet spot to be, why is it still that the testers are very low and that you can beat the curse of dimensionality? Okay, so that's for the remaining of the talk, that's really the question. What is the structure in the data that make them learnable? And to think about that, it's useful to think about the fact that I have several, learning regimes, and I can ask this question in those different regimes. And it's very simple empirically to move along this. You fix the width of your network, and you change alpha, and you measure the tester. That was, I think, one question that was maybe asked. And for modern architectures, we and others, and Nati and others, found that I think what everybody expects, which is that it's much better to learn features. Okay, so I think that's clear, and I think this is a big also question to understand what is really feature learning doing for modern architecture. But what we found, and that's for gradient descent, if you start to play with SGD, sometimes those results change, but for gradient descent, when we looked at image data set, and again, the team in Google confirmed that, what we find is the opposite. We looked at, fashion MNIST, Sci-Fi 10, things like that. What we found is that it's better not to learn features. And I think for practical implication, we don't need to care about that because fully connected nets are very poor networks. But I think it's interesting from the conceptual viewpoint because many of the theories that seek to understand the benefits of, learning feature, well, they look at fully connected nets because they are easier, to think of. And so for images, I mean, for some data, it may be a good viewpoint, but for images, it's debatable that it's a good starting point because this is not empirically found.
So I'm surprised a little bit by the numbers, at least on the left. Like I would imagine that the gap between, say, a kernel method and which is lazy, and the
could be much larger.
Would be larger than just 2%.
Yes, I think it's also because to get this plot, we don't look at a huge number of data. It was not the maximal size of Sci-Fi. And also, we don't look at a supermodel. Maybe it's a 5 layers. So I do think that the gap will be much more significant. But so I will propose an explanation for that later in the talk. Why is it that for images, fully connected nets perform better when they are lazy? Okay, so let me go to this curse of dimensionality problem. So remember, what data should not be learnable, so they must have some, some structure. And what is this structure? And here I'm giving 3 possible candidates that are discussed in the literature. And one is the notion of locality. So maybe I want to distinguish it from something that I was told you have been discussing, which is imagine my input is highly dimensional, but only a few coordinates matter, but always the same. Okay, so this is not what I mean by locality. Okay, so by locality I mean maybe it's very important to be a dog instead of a tree to have an eye, and an eye is a local object, but this eye could be anywhere on the picture, right? So it's not like I'm saying that only a few pixels matter. Okay, so there is this notion that locality in space, small feature can be important. Another idea, which I think is quite related to the first, at least easier to think with the first notion in mind, is that of data being combinatorial or hierarchical. So if I am a dog, it's because, so to be an eye, maybe I need to have, 2 edges and a circle. But then to be a face, I need to have 2 eyes and a nose and so on. Okay, so it's combinatorial in this sense. And I'm not referring all the works, and I think even Marc Mézard talked to you about that. So one idea that this is really important. And there's another idea which sounds quite different. I mean, Mala and Bruna thought about that early on. And it has to do with invariance. So if you take a cat and you translate it, it's still a cat. Problem is, translation of images is just 2 dimensions. You're not going to reduce the dimension a lot. But they argue, well, you have more invariance because if you do a DFEO, so a smooth transformation of a cat to your brain, although the image can shift a lot and acquire a big distance, to your brain, this is still a cat. Okay? I will tell you how we generate those cats. And so is it true or not? I mean, is it true that it makes data learnable?
Sorry, transformations in what space?
So this is now, forget about the weights. So now you take the weights infinite and so this is input space. So this is a cat. And then you take a smooth, if you're a physicist, a displacement field, like each pixel you move them to another location. And this displacement field, a diffeomorphism, you take it to be, okay. So to each pixel, you allocate it to another location. You distort the picture, yes? So a DFEO, right, go from, so now you can think about, Z1, Z2 has 2 coordinates, and you have a map that associates to a point, another point.
So this cannot reduce the dimension by that much, like the space of transformations, because think of you can encode a very hard combinatorial problem, for example, as say 10 by 10, like 100 balls that are very separated and are either red or blue, and you can encode a very, very high-dimensional combinatorial problem, and after you deform, it will still be the same encoding, right?
So can you say again? Sorry, I didn't.
So I'm saying you must have other properties of natural images that are not just transformations, because transformation by themselves, I don't think they can reduce the dimension to so much that you couldn't encode. You could encode an unlearnable problem like by say suppose you had you encoded an instance of a problem by putting a checkerboard with each box being either blue or red, and whether it's blue or red, that determines the binary string, and that binary string is the input to your problem. So that seems like a representation that would be pretty robust to all of these transformations that you put here. You would still be able to.
So you have a checkboard? Okay. I would love to, maybe I can post, maybe it's the question time, we go through it. Yeah, or dinner time. But I think, those are important.
Sorry, I just wanted to clarify one thing. So are you saying if I do a rotation in pixel space, the image should still look like that?
So if you do huge DFEOs, that you can probably completely, at some point you will lose the notion of a cat, right? So this is for small transformations, they argue. Yes. So if you make giant transformation at some point, it could. So essentially, I think the idea is that who you are, being a cat or a dog, if you move along DFEO, has much less probability to change than if you move in random directions. But if you, yes? So what we'll do later on is to test this idea by looking at small DFEO and looking at sort of linear. So if you go in direction of small DFEO, how much your predictor is sensitive to those directions. Yes?
How is this different from Lipschitz?
From what? From
Lipschitz of the target function.
Well, it has nothing to do because here you have the notion of two-dimensional space. Right? Lipschitz with respect to what?
The input space.
Well, once I will be talking about stability, once I will be making a statement. So this is, okay, so it comes in the next slide. I look at the definition and you will see the difference. but essentially, Lipschitz is looking at f of x minus f of x prime, something like that. Here you will look at f of tau x minus f of x. So you will look at certain direction in input space, not all of them. And those three ideas that are proposed, they are sort of natural guesses knowing what, deep learning, the good architectures are, because they are CNNs. And as you know, they have the notion of locality because they have local filters. They are deep, and it's known that if you're deep, you can easily actually express combinatorial functions. It's not known that you can learn them easily. And also, they are translational invariant. You have weight sharing, so at least you enforce that if you translate the image, you get the same answer, which is not the same as stability to differ, but it's sort of related. But I think this question is still completely open. Which of those three ingredients are really central to actually understand how you beat the curse of dimensionality? And if the three are important, is there that, one is more important than others, and so on? Okay, so what I will just be telling you is what we we don't have the answer to this question, but what we are trying to do to think about them. And for 1 and 2, I will be, I think our approach to that is to try to be quantitative, and as empirical people who like to do empirical studies, one aspect that you can measure are the training curves. What are the exponents that relate tester and the size of the training set? So for those two first points, we'll try to come up with models where we can control the structure and decide what's the training curve. For the third point, actually, this will be essentially completely empirical. Okay, so actually, Alessandro and Francesco are in the room. So this is our work for locality in the lazy regime. So here, okay, forget about classification. We'll be looking about regression. And you're trying to actually estimate some target function f star that's random. It's going to be some kind of random Gaussian field in this problem. Okay, so this is your tester. And this is how we define the locality of the task. So to simplify notation, think about a one-dimensional image. Okay, so it's in D dimension. And we will define patches. Patches are just adjacent sets of coordinates. Okay? And an important variable is T. T is the dimension of the patch. And we will define this notion of locality, saying the true function is just a linear sum of functions that can vary. This function can depend on the patch that you consider. But it's just depend on this patch variable. So it's a sum of functions that all function depends just on T variable and not on D variables. Technically, we take GI to be a random Gaussian field, and we control the smoothness of this field. But I'm not going to enter into any detail. So it's a teacher-student framework, right? So, you have, this is a teacher, you're trying to learn that, and the way we will, the student, what we'll do is use a kernel method, but you can think of it, it's a bit more general, but you can think of it as the NTK, the neural tangent kernel of a one hidden layer CNN, okay? Which has also filter size that also has a notion of locality, but this can be different. I call it S. Okay? So the data you're trying to learn is T local, and your student has a prior locality, which is S. Yes?
So in the CNN, usually I do the same filter for all those units, but here, in the definition of F star, there's a different filter applied in each location, GI, right? There's an index I.
So, okay, this is the target function you're trying to learn. So,
You said the student is the
Well, the student is, the student think about no, it's just a kernel that you will obtain from an infinitely large
No, so
one.
in this convolution network, on each one of those nodes, is it the same filter or different filters? You have D filters there. Are they all D filters the same, or are they different filters?
No, so you do the usual thing that you take a random initialization of all your weights. You have an infinite, you take this limit to
But
be...
the weights are all independent. They're not tied. Not independent initialization. When you're doing training, the weights are not tied with each other. Each
Yes.
weight is separate.
We just use a kernel method, which is an NTK of a network like that,
Of a network like this, where the weights are
with an
separate.
infinite number of weights where the weights are...
The weights are separate, not the same.
Yeah.
Weights in infinite. Okay.
Those weights are separate. I mean, we'll talk about weight sharing in the next slide, but that's it. And you can solve this problem. I mean, we do it using physics-based method, but I mean, actually, you can also use source capacity, ideas for. Essentially, what you have to do is to diagonalize the operator defined by the kernel. And I'm just going to give you the answer. So what we get for the tester is that it actually decreases as a power law. That depends on the smoothness of the function you're trying to learn, divided by the size of the filter. And this holds only if the size of the filter is larger than, the locality of the data. Because if it is smaller, for this game we're playing, you cannot learn it. So the tester will actually go to a constant. So, so what it means in particular is that the data structure I looked at is not that simple to learn. For example, if you were trying to learn it by a fully connected net, S would be D, and actually you would hit the curse of dimensionality.
So that's actually interesting in the sense that you could imagine that a non-lazy regime, that could be a separation between a lazy and a non-lazy regime, where in a lazy regime, if you don't have the fire, you will be dead, and in a non-lazy, you potentially could learn that and adapt to it.
Exactly. So I will tell you in the next slide about a hierarchical CNN, which spontaneously adapt to locality, but we're still lazy. And you're asking a question that we're thinking about, but in this context is not understood in my mind, which is how, in the feature learning, how can you learn locality from scratch? Which is an interesting question because people with dropout and complex dynamics actually do see that they can learn from scratch this locality. But here I'm not going to discuss that. I think it's a pretty open question in that case. For the other definition of locality, which is just depending on a few pixels, that's much better understood. So what you find is that, yes, if you don't have the good prior as a student, you will be cursed. You will not be able to actually do the job. But if you have the good prior, if, D is much larger, the best thing to do is to take S to be equal to T, and then you have a favorable exponent that does not go to 0 if you take the limit D going to infinity. Okay? In this simple model, you can, I think that was Nati was asking, you can also add weight sharing and impose that both the student and the teacher are transition invariant. And then what you find if you do this is a very mild gain. And this gain is equivalent to multiply P by the dimension D. And there are general arguments as to why it should be like that. So what we recover in a simple model like that seems actually to connect to what's found empirically. So for example, there is this study here where they looked at a CNN acting on images, and then they removed weight sharing, so they killed transition invariance, and it cost little, it doesn't change much performance. But if you make the filters much larger, you completely lose performance. Okay, so that's also what you would see in a simple model like that. Okay, so yeah, locality seems to be really important. That's supported by this model, but clearly a model like that is too simple to really characterize data. I mean, data are much more than just being local in the way I define, and one way to think of it is my student network, if I was acting on real data, will still give very poor results, right? So this is submitted work, not yet on the archive, is essentially to extend that to hierarchical CNNs. And so we look at CNNs where actually the patches have no overlap. So it's like it has the structure of a tree. Now each node here, think of it as an infinite number of hidden neurons. okay, a very large number of hidden neurons. So we look at CNN of that types. And again, so what we did here, and Francesco was the driving force behind this calculation, is to diagonalize the neural tangent kernel of networks of that kind. And once you have that, you can again use those arguments, replica method or source capacity arguments, to actually predict what should be the training curve. And the key result that we obtain is that if the task is T-local in the sense I defined before, or if it's a function of just T-adjacent variable, and in the paper here I'm just showing the result for very large T, but we have the correction to that. But what you find is that those neural tangent kernels are essentially adaptive. So before, I would need to, to really have a good result, I would need to choose to know a priori how S was related to T and to take S equal T. Whereas for those networks, you actually don't need to do that. They perform from scratch essentially optimally. Okay, so those hierarchical networks, they can guess what is, they're adaptive. They can perform well independently of how local the system is. They don't need to know it a priori. So there is also a sort of interesting negative result in this approach, which is what if you were thinking of this as not a student but as a teacher? So you know that if you take random weights in the infinitely width limits, you generate a random Gaussian function of known covariance. And it will have some hierarchical structure. But so what you find is that even if you learn it optimally, so the best thing to do is to take a corresponding kernel as a student, you find that you hit the curse of dimensionality. So as a teacher, there's not enough structure there to actually make it learnable. So it means if you want to explain how the curse of dimensionality is beaten, this is too rich a model. You need to constrain the data more. Okay. So they would, So there are some ideas in the,
What are the parameters of this probability distribution if you think of it as a teacher?
So if you think of it as a teacher, it's just that you randomly initialize the weights. And so,
Infinite weights?
Sorry?
But like you randomly initialize the weights?
So in the limit of infinite number of weights is converged to a Gaussian field.
Okay.
But it has a covariance that will know about this spatial structure.
I see. Okay.
Yeah.
So it's just like, so it's information theoretically there's just too many parameters to...
Well, the argument we make is we use this method to compute, in terms of Bayesian, the best thing you could do if you have a random Gaussian field is to try to learn in with a kernel that has the same covariance. And so if you do that, you get this result, and you cannot do better. So this structure is too rich. Okay, so now, so let me go to the last point, which is this idea of stability to DFO. And now we really want just to empirically try to measure if there is evidence for that. Is there this idea has been around in the literature, but there is very little evidence that it's actually important. And so what we did is to generate a set of random diffeomorphism. So the way we do it, for a physicist, you can think of it like that. You just take every pixels to be a node, and you put little springs connected to nearby pixels, and then you put temperature. Really, what we're doing is that we have this DFO, and we define a norm. Actually, it's the L2 norm on it, gradient of tau x square integrated. And then we look at a maximum entropy model. So we look, if you want, at a flat measure on all DFO which have this norm. And in a canonical ensemble, you can think about temperature. So this is a cat that's hotter and hotter. If the temperature is small, then with extremely large probability, you have a DFO. If the temperature is much larger, then it's not a DFO anymore, and you start to have singularities that pop up. And then what we do, okay, that's the question about Lipschitz, so that's not Lipschitz. What you define a sensitivity to DFO. So you define a sensitivity to DFO. What you do is that you deform the image, and you see how much it's changing your output. And you can look at the output, or you can look at the internal representation within the network. Okay? You square it, and you average it on different data. And now you have an ensemble of DFOs, so you can average on many, many DFOs.
Did you check with your students that they really did this? Because it looks like they just put the cat in the oven and check it.
So actually, at the end, it's very simple to solve. In physics, it's a free field. So you just have to take random Gaussian numbers. So it's actually extremely fast to generate those cats. So I don't think that would have been more complicated to put them in the oven. And so here is the key result that was obtained. So what was done here is to look at the last 15 or 20 years, the different networks that were proposed. So here are the modern one, and here are the old fully connected. This is LeNet and so on. And after training, this is for CIFAR 10. In this paper, we look at different data. And what you have, it's a log-log plot. What you have on the y-axis is the performance of those networks, the testers. So the best networks are low there. And here, what you have on the x-axis is actually the sensitivity to the smooth transformation. That's what I call RF. So if you're over there, it means that you're very sensitive. Okay, in our units, if RF is 1, it means that you're you're equivalently sensitive to DFO or to random direction, which would be Lipschitz construct. And so that's the key empirical result of this part, which is that you have a very strong correlation between the two. So the best network precisely seem to be those which are very insensitive or stable. They are very stable to smooth transformations. Yes?
How do you measure our...
So what you do is that you train your network, and once you have it post-mortem, you deform the image in many ways. It's like spectroscopy, like you deform a little bit the image, you see how it's changing the output.
Average over in data set.
Yes, so there is an average on all the training set, or you can also do the test set. We find consistent results.
And this is the vector of soft probabilities?
Okay, so yes, I think it was not binary classification there. Leo is not around, unfortunately. so it was, right? Yes.
Like the 10-dimensional.
Yeah, yes. Yes. Yes?
Is there a sort of ground truth or control experiment to compare this to, where you do the same thing with like some random direction?
So in fact, we defined. That's why we defined the RF like that. So since I'm running out of time, but the idea was, in the paper you will see that the definition of RF is we normalize it by f of y by the Lipschitz constant, if you want, using that a point y and x that are at the same distance as tau x and x. So you look at random directions.
So that's why it's one at initialization.
It's actually one at initialization, and I think but it's not obvious that it's one. Yeah, it's one at initialization because the most modern architectures, there are very little pooling. And so they don't care about. They have to learn to be stable to smooth transformations. Yes.
But then this also has a negative side, right? Just because a small r means that like the adversarial perturbation can be much worse than this random deformation.
Can you say it more?
A small r would also, when it's normalized by the Lipschitz constant, it could also imply that the adversarial perturbation can be much worse than this nice deformation.
So it's actually true. So if you look so we did study that quite, in this paper, we study systematically stability to differ with stability to noise. And it is the case that the best network are the least stable to noise. So actually, the two, you would still have a good correlation with the RF, but you get a much better correlation if you derive it like that.
So is it the case that if you didn't scale RF, then now it's a little bit, it's a question of what is the correlation, right? So RF could go down for two reasons, because the networks, these networks are more sensitive to random changes, or because they are less sensitive to these.
So we do quantify in the paper really both. And we find, you would still find a correlation, but it's much better if you use this one. And to us, it made more sense, because I think it makes sense to have something that doesn't have any dimension. You compare how I vary in interesting direction versus how I vary with respect to random direction. So I think that's what we did and did not publish, what we did recently is to try to see, can we change, this sensibility to noise, can we actually change it if we add noise to the data? Okay, these are other directions, but yes, in the paper we argue that the correlation is always there, but it works better here. And we propose some explanation as to why it should be like that.
Sorry, did you try, in this picture, these are all real neural networks. Did you try to put some kernels on this picture?
Yes. So you will have those kernels in the next slide. But in general, even if you look at scattering transform of Mala and so on, they are, sort of there. So, yes. So maybe that will also answer this question. You can look in depth how you become stable to differ. And in those networks, it's not, if you are in the lazy regime, it would only be at the last layer. The representation is essentially not changing. Here, it's completely a feature learning regime, because you see that RF, if you measure it internally, it decreases from the output to the input. From the input to the output, yes. So it's really you're changing the representation of the data. Yes, and all this is learned. Okay, so, so now we're trying to understand that more quantitatively, and maybe I would just tell you how we're trying to think about that in 2 slides. And I'm already over time, so I wanted just to go back to a question I raised at the beginning, which is, why is it that fully connected net perform less well on images than in the lazy regime? And here is a plausible, I hope you would think, explanation. So those fully connected net, actually, they are precisely those that as you train them, they become less stable to differ. They become more sensitive to differ, actually. So you see that RF is much larger. It starts to be quite larger than 1. So you have this property. You have another property, which I told you earlier, that feature learning is detrimental for them. And that suggests a causal relationship, that maybe learning features for them is not so good, because when you are in this regime, you start to become very sensitive to smooth transformations. So one data that backs up this idea is that, as was mentioned, for those fully connected nets, you can also study the lazy regime. So nothing will happen inside if it's a deep fully connected inside of it, but at the output, things will happen. And what you find systematically is that, yes, in the lazy regime, actually you are less sensitive to differ. And so the question then is, why is it the case that, so this strong correlation suggests that it's actually important to perform well, to be quite stable to differ. Why is it that fully connected net don't do that? So here's what we argue. We argue that if you have a fully connected net, and you're trying to, and you do say regression, and you're trying to, okay, it's that's where we could really work out, but it's more, we think it's more general. We think that if the function that you're trying to learn is smooth along certain direction in input space, then the feature regime has a drawback. For reasons that I think Nati, so we have a paper on arXiv on that, for reasons that Nati discussed earlier, I believe. So often when you learn features, when you're in the feature learning regime, what you can obtain is a very sparse density of neurons. Many neurons start to do exactly the same thing. And you can really have something very sparse if you impose some kind of weight decay, maybe L1 weight decay or something. Or, as you were told, I believe, you can also get sparsity if you initialize the weights to be very small. Okay? What we look at a setup where inputs lie on the sphere of dimension D. So here it's just in 2D, so those are data points. And we looked at the setup where you try to learn a function that's very smooth. We look again at a random Gaussian field, but here, just think about even a constant function. What you can argue in this setup, at least when you do L1 regularization, is that the number of effective neurons that you get after training should not be larger than the number of data points. And we do find that, and actually even when we initialize the weights to be very small, we also do find that. Okay, so this is the direction of the neurons. So initially your neurons look in all directions. In the lazy regimes, they will still look in all directions, but in the feature regimes, they would collapse and act just as a few neurons. Because you just have a few neurons, the function you're going to generate is going to be very rough. Okay? And so what you can show is, for example, okay, we go beyond that in this paper, but just as an illustration, if you try to fit a constant function, constant along the circle, what you find is that in the lazy regime, you have much better performance than in the feature regime. The difference diminishes as the function you're trying to fit becomes rougher and rougher, and at some point of roughness, then the two are equivalent. Okay? So learning sparse features leads to rougher, less smooth predictors. And so the idea is that if for images you really have direction like along DFO where the task needs to be quite smooth, learning features then is detrimental. Okay, I was going to, now I'm super much over time. I was going to tell you how we try to think about what happened on the rest of the curve, but I will just keep it for private discussions, and just maybe conclude. Okay, so the first 2 points you guys discussed them already. I mean, so should we be afraid of bad minima in the loss landscape? So no, you just crank up the number of parameters. You will undergo phase transitions, this jamming transition, but once you're past it, no, you cannot get stuck in a bad minima. Should you be afraid of overfitting? No worries again there, because you do converge to well-defined algorithms, and then you have this noisy convergence due to the randomness of initialization. You can get rid of that by doing ensemble average. What about the curse of dimensionality? I think this question still completely stands. What I've shown you supports that notions like locality and stability to smooth transformation are actually key to performance. But I think it's really a direction where we completely lack models where, that would have these hierarchical properties, but also the stability to DFO, to try really to understand what's behind this puzzle. Okay, thanks. Sorry for being long. I will take questions if there are any. Yes?
On this slide, you were showing the stability diffeomorphisms for kernels versus fully connected networks.
This one?
Slide before. It shows the same slide with increasing number of samples. Fully connected networks can also have lower sensitivity, lower sensitivity or more stability. So it also becomes, I think, sample complexity is entangled in there as well, right?
Yes, so we don't see it. Okay, so maybe it's a bit in the noise in those because this is a variance. So maybe it seems to be the case here. So I think that yes, completely. So yes, so the number of data is actually affecting this this stability to differ. And maybe if you have a huge number of data, this effect disappears. Right. So now okay. So I think this maybe your question is it also the case in the model? I think in the model. The difference between those two curves in very simple models where you look at a constant function on the sphere, the transformation that would play the role of differ would be rotation. And so the difference between those two curves would be very much related to the difference of test error. Okay, so okay, I mean, I think real data are more complicated. For example, for MNIST, this difference seems not to vanish, and for the others, it seems to do. We don't really know why. Yes. Yeah, I mean, I think real data are quite complicated. I think this is a plausible explanation of what's going on, but to really capture the details of that, I think you have many effects in real data. So another effect that will play a role is, I think feature learning has some drawbacks, but it clearly also has some advantages. For example, if you have pixels on the edge of the image that are unrelated to the task, it's better to learn that they are unrelated. So I think it's also the tester at the end is a combination of different effects. And so it will be hard to be quantitative because you have to sum up different things. But this effect of being bad is clearly there, I think. Yes, thanks. All right, other questions? No? Okay, thank you all.